In the extreme case, if you have a model with 0 parameters, you just said this is my function. If you modify the test set or the training set, it does not. More generally, it subsumes the degrees of freedom. It also subsumes other properties that come up in neural networks, which make neural networks generalize better, which don't necessarily require reducing degrees of freedom or restricting parameters. And the reason you care about stability is that if the algorithm is stable, there is no overfitting. So that's one piece of the puzzle. The other piece of the puzzle is good training set performance. So if you have an algorithm which is stable and you are able to fit it to your data, then you will get it will be good. It will be good on your test data. So it's important to remember that there's always these two components. You can make an extremely generalizable algorithm, but if it doesn't fit your data, it's not going to fit your test data either. And in all the examples of regularization, you can think of them as improving stability. So changes to preprocessing, changes to your model, or changes to your training procedure will make your final result less sensitive to the original training set. And that guarantees better generalization. So, okay, so here's a, so basically here I'm sampling different points and I'm fitting a line and I'm fitting this 6-degree polynomial. So you can see, actually here's a better one. So you can see that when I'm fitting a line, changes to my data set does not generate big changes to my final model. However, when I'm fitting a polynomial, changes to my data set give large changes to my model. So in that sense, the first, the line is more stable algorithm, and this is less stable, and we expect generalization to be better in the case of line. Any questions?
What do you mean by small changes? Like, you know?
Right, so small changes, you have to think about distance between functions. And the most practical way to measure changes, if I were to measure it in practice, I would say this is, so I have some function. You can basically measure it at a set of points, and that gives a vector. So this is 0.5, this is say 0.7. So essentially, this will generate a vector. So a practical way of measuring how close the functions are is to discretize it, measure their values, and then just take Euclidean distance between these two vectors. So, but yeah, that's a good question. When I talk about changes to model, you have to look at the distances in the model. And a way to measure those distances in practice would be to just evaluate this model at some grid of points or some random set of points and treat those measurements as Euclidean vectors. However, people have thought hard about more natural way of modeling distances. So for instance, if your functions are probability distributions, then there is a natural measure called the Fisher information method. So that's a way of measuring how far two distributions are. Okay, so in the intuition, where do we care about stability? Does this make sense? People say it's bad to read your own slides, so just. So that's the intuition. In the learning literature, there is a whole theory of learning where they prove bounds, but essentially that's the intuition. Okay. So how do we make our fitting procedure more stable? So we can reduce the number of parameters, or we can restrict the ranges. We can make our optimization procedure not very good. So essentially, if our optimizer is very good at finding the minimum, then it will be sensitive to the data set. If it's really bad at finding the minimum, it will be less sensitive. Sort of makes sense. And also you can add, you can take a data set and you can add additional constraints. Okay. So a big part of the book. So the book starts talking about L2 regularization, and then later it talks about constraints and how constraints is actually a form of L2 regularization. So I'll start by talking about constraints because actually that's more motivated. We know that if you constrain some parameters, you make things more stable and you regularize better. So does everybody know what L2 regularization is? Essentially, when you train, you add this squared, you penalize by the square of your sum of squares of your parameters. However, there's an alternative derivation where you will see that this comes out if you want to minimize your loss while constraining your parameters to be to have particular value. So here I have a 2D optimization problem, and the green disk, the blue disk, is my constraint. So the constraint is sum over I, wi squared, less than or equal to 1. And doing it backwards. So I'm minimizing of G of W subject to this. So in this, this is inequality constraint problem, and there are two potential cases. One, if the constraint is active or the constraint is not active. So the second example, the constraint is inactive, meaning when you minimize this problem, it's already satisfied. So when the second case is true, it's as if we don't have any constraint at all. So it's easy to solve. Now in practice, when you constrain, so with auto-regularization, the first case is more likely. And when constraint is active, essentially the solution is on the boundary, and this inequality becomes equality. So how do we solve this problem? So to solve this problem, it's a technique called the Lagrangian. You basically introduce an extra variable. So we have W and we have lambda. And we have this Lagrangian, which is JW minus lambda I squared.
Do you want to try a different marker?
Yeah, sure.
This one is like, looks like it's done.
So this is a general technique. Whenever you have some kind of constraint optimization problem, you create this Lagrangian, which is the original term, and then lambda multiplied by the constraint. So this thing, you can rewrite it as sum of I wi squared minus 1 equals to 0. So that's the thing that goes in here. So the solution to this optimization problem is the solution to gradient of Lagrangian being equal to 0. So to solve this problem, you have two sets of variables. So we want to solve W is equal to 0, and then we want to solve lambda equals to 0. Yeah.
So there is a constraint on lambda also. It should be to the 0.
Well, so I'm here. It's a constraint optimization problem.
Yeah, there's a constraint on lambda also. It should be greater than 0.
For constraint optimization problem, I think this is only for inequality. Then when you solve this this Lagrangian equal to 0, it's already constrains you enough. So, but yeah, if I actually didn't break it into two cases and I wanted to do it as a single optimization problem, I would have this extra constraint. So here
that would be fixed.
Yes, exactly.
I think you at least need lambda to have a common zero. Right, you're essentially saying that those level curves of the function and the level curves of the constraint.
Inequality constraint is simply differentiating Lagrangian and setting it to 0. So if I differentiate with respect to W, I get dj plus 2 lambda W. Let's say this is it's a vector. And this is a vector, and I'm saying it's equal to 0. And then I have some extra things. So now suppose I have already solved, I had some method and I already solved and I found the optimal lambda. I can plug it in and then just say lambda opt. So, and now suppose we have a function g such that gradient of g is equal to gradient of j is equal to let's see, g is equal to j plus this one lambda. So alternative, so solving this equation is equivalent to solving the dg is equal to 0. And the way I can solve for this gradient being equal to 0, I can take and I can simply minimize g. So essentially, the important thing to remember is there is some value of lambda which you can plug it in, and it will give you that solution. So in other words, when you solve this L2 regularized problem, there is also some constraint problem which is equivalent to it that the answer would come from. Okay.
One question about
Yeah.
the Lagrangian.
Mm-hmm.
Go back one slide.
Sorry, what?
Go back one slide. So
Here?
yeah. So the Lagrangian active derivation is farther away from the global minima, while the inactive derivation is closer to the global minima.
So the inactive one, the solution already lies inside the disk.
Okay.
So essentially, this constraint, if I remove that disk, it wouldn't change anything. So in the case of active, the solution lies on the border. In the case of inactive, the solution lies inside. So if I remove the disk, the solution would not be effective. Okay. So in section 7.1.1, he goes over the exact solution of regularized linear regression. So on the left, you see the standard formulation. You have a linear least squares problem. That's the first line. The second line is you can write this in matrix form. And this one is the solution of minimizing that function. Similarly, in the second column, you can modify the first line is the modified function, the second line is the modified function in matrix form, and the third line is the solution. So, and it can be derived by essentially differentiating that expression. So the expression with matrices, there's essentially differential calculus, which looks very similar to regular derivatives. So it's basically like 5 lines of algebra if you do differentiate this second expression to get the answer. Yeah?
Is there any point to change the alpha while you're searching for the minimum, or you keep alpha constant?
Yeah, there's definitely, it's a very important parameter.
But is it always constant once you start optimization, or would you
Oh, I see.
change it during optimization?
Yeah, there are some papers where people start with a large alpha. So essentially, when you have a very large alpha, when you regularize a lot, your problem becomes much easier. So if you look at the case of just analyzing with the sum of squares, if you just have a huge alpha, you're just minimizing this quadratic pole. So you have a very simple minimization problem. So people sometimes start with a simpler problem and then gradually make it more complicated. One issue here, though, is remember, it's not enough to just regularize. You also want to fit your training data well. So you want to prefer regularizers which push towards the functions which you expect to be good. And there's evidence that just penalizing just sum of squares is not the best thing. If you think about it, why should we want all w's to be 0? And recently, ResNets have been quite efficient. And essentially, what you have in the ResNet, when you apply the L2 norm regularizer on the ResNet, you're essentially encouraging functions which are identity functions. Because in the ResNet, so in the regular network, you have something like activations of the next layer is equal to activation function times W activation y. So this is regular network, and then you can penalize by Frobenius norm squared. So basically sum of all matrix coefficients. So that would prefer small matrices. But maybe instead of preferring just small matrices, you want to prefer functions which are identity. So in the ResNet, you have something like I plus W. So now you can see in this formulation, this regularizer, it's actually doing something different. It's actually pushing your function towards the identity function. There is a paper that came out recently. It's called Identity Matters. Matters in Deep Learning. Matters in DL. And they prove some very interesting mathematical results. Essentially, they're saying if you have this form, if this penalty is high enough, your problem becomes convex, and they're able to have very deep networks that they're able to learn. So that gives evidence that maybe you care about preferring identity functions rather than just functions with small coefficients, and that's something you should always keep in mind. Okay, linear regression. Oh, so I'll give a simple example. Okay, I remember what I wanted to show. So suppose you have this this problem where you have 2 points. You have a point at 0, 0, and the y value is 0, and then you have a point at 1, 1, and the value is 1. And you're trying to use linear regression to fit a function which fits these points. So you can see in this case there is actually an infinite number of planes that fit it. So does it make sense? So let me just make it more concrete. So I have a data set x1, x2, y. So I have 0, 0, 0, and then 1, 1, 1. And I want to learn a function which fits this data. So my x function, x matrix is 0, 0, 1, 1. And my y matrix is 0, 1. So now, if you plug in this formula, so in the earlier slide you saw there's a formula how to solve this, and you will get an error. It's a singular matrix. You cannot invert it. So that's essentially the mathematical telling you that there is not enough constraints. And you can see there is not enough constraints because there is a whole range of functions which fit it. What you can do, you can add constraints, and if you add this L2 slash constraint optimization, you have the solution here. So alpha is my regularization parameter, and you can see if I'm making it smaller and smaller, my parameter vector is approaching something. So if I take the limit of this alpha going to 0, what I get is a pseudo-inverse. So if I use pseudo-inverse to find the solution will be 1/2, 1/2. Which essentially picks a plane which is between these two planes. Does it make sense? Okay, so that was L2 regularization. Section 7.1.2, it talks about L1 regularization.
I think if you'll hit play, it'll just take over the whole screen.
So L1 regularization, this is what the function looks like. if you view it as a constraint optimization, the contours essentially look like this. Whereas for the L2 norm, if they were circles. However, there is a more important property of this L1 regularization, is that it actually encourages weights to be zero. And you can see why that would be from this picture. So suppose I take a projection, one-dimensional projection. So this curve here is my loss, original, actually. This is my training area. And this is my L1 regularization term. So you can see here that if the loss is not very steep, essentially I'm going to always get stuck at zero. Essentially, if loss gradient is smaller than the gradient of this L1 loss, you can see I can make a step in that direction. I'm trying to minimize the sum of these two terms. So if this loss is not very steep, taking a step in this direction will incur a loss increase, which is higher than the loss decrease I would get from the decreased training area. So this is a very special property of L1 regularization, and it's also known as shrinkage for this reason. And what happens is that when you train models, what you often see, some weights kind of get shrunk to zero, and then they get stuck at zero. Make sense? L2 regularization does not have this property. And the reason it doesn't have this property is because for the L2 regularization, it's essentially a square function, and the gradient is zero, so it's completely flat. So you can always move a tiny amount to improve your loss, unless your loss is completely flat. In the end of the L1 regularization section, he talks about how L1 regularization is equivalent to this Laplace prior. And essentially, this connection to map is if you treat your inference procedure as trying to find the value of theta, which maximizes the value, which is most likely using this Bayesian principle. And you see there are several terms here. When we care about optimizing over theta, this log p term is constant, so we drop it. So essentially there's two terms. There's the theta likelihood, and then there's the parameter likelihood. And then if you take, for instance, if you take the Gaussian, if you say I believe my parameter theta is around zero, and your belief is a Gaussian with some standard deviation. So if you plug in the Gaussian centered at zero here, you will essentially get a squared norm penalty. And what he's saying, if you take this Laplace distribution and plug it in and take the logarithm, then you will get this L1 penalty. Does it make sense? Okay, so in section 7.8, he talks about early stopping, but I think it makes more sense for it to be earlier because it is directly connected to the weight decay. So what can be shown in what he goes over in the second half of it is early stopping is equivalent to constraint optimization. And the way you can see it is here, if you're starting at zero, and you stop immediately, your parameter will be 0. That's as if you're constraining it to be 0. However, if you start at 0 and you take very small steps and then you stop, you will be somewhere here. So essentially, you can control how far you're going along this curve, and if you stop early, you essentially will be within some distance of the origin. And this sounds very hand-wavy, but in the page 244 and 245, he's actually deriving, he's actually proving it. Questions?
I didn't get that. Is there something good or bad?
Early stepping is the same as constraint optimization or this L2 norm penalty. However, it's good because it's very simple. Essentially, what you do is so the problem with L2 norm, there is this extra parameter. So this extra parameter lambda, and it's actually pretty important. So if you set it too large, you're essentially ignoring the data. If you're setting it too small, you overfit, and you typically have to do something to pick it. However, with early stopping, there is this very natural way of using it. So essentially, you look at your validation set, and you see here your training error keeps decreasing, but then your validation error is no longer decreasing. So that's early stopping. You just say it's no longer decreasing. This is I stop here. Yeah.
Does that result, like you said, if you take very small steps, right?
Mm-hmm.
So it's asymptotic. It's an asymptotic result.
I didn't read too much into it, but I would expect it would be something like that.
Okay. So, but then maybe the trade-off is probably it's going to be easier to compute the L2 norm. I mean, you just plug in the number, but you have to a bunch of really small steps, right?
Well, so it's proven mathematic for math. You have to have really small steps. But in practice, you can take larger steps, and it seems to work pretty well too. So it basically is similar to L2 regularization, but it removes this extra parameter. However, in practice, what people do, they actually do L2 regularization and this thing. So for some reason, just having this L2 regularization just helps things. It can even help with your training error, which doesn't make sense mathematically, but it really does. So one issue he talks about, when you do this, you have some data set, and then you have to take part of it and use it for validation. So you're not training on it. And if you have a small data set, you want to train on all of it. So what do? Well, one thing you can do is you first train on your smaller training set and use this validation set to find the cutoff point. And then you train on the full data set for that many steps. Or alternatively, you find the target accuracy, and then you train until the target accuracy. So there's various recipes. Ultimately, it doesn't matter which you pick. You just have to pick one. Yeah.
Wasn't there like a paper doing early stopping based on when your like gradients shrunk below like some threshold?
Early stopping when the gradient. Well, it doesn't seem like early stopping. It seems like actual stopping. So essentially, if you look at the optimization algorithms for before even deep learning, like Newton's method. So Newton's method, you optimize until the gradients become tiny, and then you stop optimizing. So essentially, when your gradients are tiny, at some point you're not making any progress, even on your training error. So this is different because at some point your training error doesn't decrease, so you should definitely stop at this point. But early stopping, you see you stop here, your training error is still decreasing, so your gradients are still pretty good. But you still want to stop before you go further. Okay. going to section. So section 7.3 under constraint problems. So we covered that with the plane. Section 7.4 is dataset augmentation. So dataset augmentation is actually an extremely useful technique. So there's many regularization techniques. There's many papers about many very mathematically heavy regularization techniques. But in practice, at least when I was at Google, the augmentation is one of those things which doesn't get many papers, but it's actually used disproportionately heavy in practice. So this is an example of dataset augmentation for ImageNet. Essentially all papers that do ImageNet are now doing this. And essentially it makes your dataset larger and things work better.
There's some questions. I
Yep.
think.
Is data augmentation, is it the same as, does that have a similar effect of whitening your data, adding more than one by adding more images?
So whitening data helps with optimization. So whitening the data actually helps you to drive the training error faster to zero. Dataset augmentation, essentially it makes the problem harder. You may augment your data set, and your training error used to go down really fast. After you augment it, it doesn't go fast anymore. However, it does help with your testing performance.
Dataset augmentation for like images seems a lot easier, but how would you propose doing it for like natural language?
Yeah, it's also it's kind of an active research problem. Yeah.
How much data should be augmented as in so that it doesn't do overfitting? As in, if how much percentage, as in how many rotations or how many scales or translations should be take as a like that?
Well, the general rule of thumb, people keep adding things until training takes longer than a week, and then they stop. So basically, the more the better, but you have some personal constraints. You have something to do on Saturday, so so essentially, the more the better. Yeah.
So this is from my wife who's watching from home. Isn't there some IID assumption about the data, and if so, then augmenting the data like this doesn't break that independent assumption?
So it definitely makes things mathematically worse. So you can't prove various things, but it makes things better in practice. So it's very empirically motivated technique. And one thing we noticed at Google, we're actually able to recognize, be able to read street signs out in uncontrolled environment, various lighting, by training on synthetic data. So we just take fonts and we render it, and then train the model on those fonts, and then be able to read photographs. And what we had to do to make this possible is to add lots and lots of distortion. And one thing which is kind of counterintuitive is that adding distortions which are not in your test set actually helps you classify the test set. So there is a paper by Yoshi Bengio where they trained to recognize the NIST dataset. There's the MNIST, but there is also the NIST. So MNIST is the subset of NIST, and the NIST dataset is essentially has characters. So what they're doing, they're adding distortions, like they take 6 and then they completely black out half of it. So they're doing things which are not present in your test set, and they make learning extremely hard. But what it turns out, if you add those very hard things, it actually generalizes better. So there's no theory for it, but somehow it works. So this is example, elastic distortions. When people compete on MNIST, some people think it's unfair to have those elastic distortions because it makes it possible to take a simple feed-forward neural network without any tricks and get a state-of-the-art result. So people sometimes say we have the best result without using data augmentation.
If you like perform data augmentation on like this original 3, then you have like 30 other samples of it, will they all have to remain in like the same like fold between like training, validation, or testing? You know what I mean? So like if you include like half that 3, could you use the one that's included in the testing set, even though like the original image is in the training set?
You probably shouldn't.
Because it could like still memorize part
Yeah.
of it.
Yeah, you should probably apply elastic distortions to the test set. Well, actually, you probably apply it to the training set only. I think the test set, you should never use the test set or any distorted version of the test set for your training.
Would that be saying that you apply the same rules to validation set as well?
Yeah. Because what validation is essentially the second test set. So the same rules. You essentially use validation to see what your test set performance is. So you're essentially treating your validation set as your test set to tune another parameter, and then you throw in your validation set in, and then use the real test set. Yeah, I think an issue with the current machine learning, you often have the test set to start with, and then if you're actually training your model and you're looking at the test set accuracy, I think many people let this knowledge leak into the design. So essentially you can look at your test set accuracy, and that is done in a day, it achieves the optimum, and then you say, I trained it for a day, but you are looking at the test set curve all this time. So essentially that makes your results not as valid. Yeah.
So is that where something like k-fold validation comes in, where then you're now shifting, you do it like 10-fold over itself so that the test data, you're not always looking at the same test data, or?
Yeah, so if you do k-fold cross-validation, you have less noisy estimate. So in that slide here, you see how the validation set, it kind of jumps up and down. If you did a k-fold, it would be more smooth. So it might be easier to find that exact point.
It's not the same though, because you want to train the model, and you don't want to
See that data at all.
on data it's never seen.
Okay. Okay, this is section 710. And the alternative way to regularize things is to require the intermediate representation to be sparse. So essentially what you're saying, okay, so you have a neural network. Essentially what you're saying, we want each of those things to be, this is hidden 1, hidden 2, hidden 3. So suppose you want hidden 3 to be sparse, and what you can do, you basically have some sparsity penalty. So you train your J, G of W plus some sparsity penalty of your H's. And you can design the sparsity penalty so that when it's not sparse, there's an extra cost. There is this course by Andrew called Unsupervised Feature Learning Deep Learning, and the exercise there is to train a sparse autoencoder, and essentially they train autoencoder which reconstructs MNIST such that only a small number of intermediate units is active. And it's essentially, it's a simple penalty you add to your cost function.
So like if you were to rate the regularization, it'd be like L2, you're going to have a whole bunch of weights. Basically like, this would be further from L1 regularization. L1 regularization you also end up with like almost a sparse.
Well, so L1 regularization that applies to the weights. This one it applies to hidden units. So can you do L1?
I guess I'm thinking back to like lasso regression,
Uh-huh.
and I view those as kind of like L1 and also similar to sparse representation regularization.
Right, I haven't seen people try to do L1 on the intermediate units. What Andrew was doing, they had a penalty where he calculates the average number of activations. So essentially, there's a sparsity target, SP target equals, let's say, 0.1. And then these hidden units, if you use sigmoid, they're all non-negative. So if you add them up, so you do 1 over, there's n of them. So you do 1 over n times sum over h. That gives you the average activation of the unit. So the penalty he does is this KL divergence between this and 0.1.
Wait, 0.1 a constant?
Yeah. Because you add them up. So you add up the sigmoids and you get a single number. And the KL divergence is for Bernoulli variable. So KL of A, B is something like E log A log B plus 1 minus A log. I guess it doesn't have to be KL, it could be like a squared norm or something. So you're basically asking that your average activation is close to some value. And what this enables him to do is to learn, it's essentially, a cool picture, essentially a stroke detector. Yeah, so this is a
On the MNIST database, it's like the strokes of the handwriting?
yeah.
Wow.
So it essentially figures out that the images are consist of a small number of strokes. Yep.
How is this similar to Dropout in any way? Because like, are there some level of activations, or like you constrain the activations in some probabilistic way as opposed to like it has to be 0.1?
Yeah, I'm not sure.
I think so.
Yeah.
But I mean, if you use like sigmoids, then it's like pretty clear. But if you use like the ReLU, then like your average number might be way off.
I just think they're kind of a different approaches to the same result of like not depending too much on any given piece of your network. Yeah. Okay.
So this has an effect of there's going to be at each layer there's going to be a small number of active units. I'm not sure Dropout would have the same effect. It seems like Dropout would be the opposite. Because if there is a small number of units and the Dropout drops them out, now you have no units. So Dropout actually encourages redundant representations. So there would be several active units that are more redundant. Yeah.
So you showed us the strokes that MNIST was composed of in the last image.
Yeah.
Back when like facial recognition was done like using PCA,
Mm-hmm.
when they had like the 42 like eigenfaces.
Mm-hmm.
Can you think of that as sort of like the eigenstrokes of MNIST, or is that not a good analogy thinking about it?
I mean, I guess this eigenfaces is linear.
Yeah.
So this is more in depth. So
Okay.
you probably wouldn't get them if you did PCA on MNIST.
Yeah, you wouldn't get these particular strokes.
You wouldn't get
Got it.
Yeah.
Quick question.
Yeah.
So it seems to more like a constraint optimization problem as well? Can we put it that way?
Constraint.
So if we put constraints on given units
Mhm.
and format like a Lagrangian,
Mhm.
so can we think it that way also?
Maybe. I mean, I haven't seen people do that. The trick is you have to make sure it's efficient, and the practical issue, because everything is just gradient descent, all the frameworks just do gradient descent. The most practical algorithm is something that just turns into something you minimize. So people that do ICA, independent component analysis, they may be doing something like this. Okay, this is section 7.7, bagging. It seems kind of an old technique. I haven't seen it used in neural networks very much. But the idea is that you take your data set and then you generate several versions of it by basically sampling with replacement. And then you train, on each data set you train a model. Those models will be slightly different. They may give slightly different predictions. And then you do a majority vote or you average their predictions. So you can see this goes back to the idea of stability. Essentially, it can take an algorithm which is not stable, which is very sensitive to the data set, and after applying bagging, it becomes more stable.
I think they were saying though that doing dropout is like kind of synonymous with doing bagging.
Right.
That's a big
Okay, yeah, I guess that maybe that's why he noted that. Okay, so dropout. Does everybody know dropout? But basically, as a refresher, every time you do a backpropagation step, you just pretend half of your units, half seems to be this most popular number, half of your units are missing. So you basically, it's one of those breaking backprop kind of things. So recently, it actually turns out there's many other ways of breaking backprop, just taking the mathematical definition and just making it incorrect, which makes things better. So, so there's a few papers came out recently which have alternative ways of breaking backprop. So you, for instance, you could propagate, do forward prop on one network, and then backprop as if it's a different network, and then it still works. So essentially, you drop half the units, and what he talks about in 7.12 is that well, that's a lot of math, but basically what you can show is that under some restricted conditions, training with dropout is the same as just training a bunch of models like this and then aggregating their results.
So dropout is kind of bagging because every time the network syncs,
Yeah, I guess.
Data, it's not the same data.
Yeah, I guess it's an extremely cheap form of bagging. So if you have n units, it's bagging of 2 to the n models. So it's not feasible to actually train 2 to the n models, but training with dropout actually has the same cost essentially. So it's a very cheap way of doing this exponential averaging of models.
And you said like you can break backprop a different way, like just by changing the backprop formula. Or can you talk a little bit more about how you break backprop and why it works?
Well, people don't really know why it works, but I mean, a simple example of breaking backprop, you do forward propagation normally, and then when you do backprop, you pretend that all your activations are linear. That's one example. or you just pretend that half of the units are missing. Well, that's actually a dropout. You can pretend that a whole layer is missing. They actually have a layer dropout that seems to work. But you can.
Untrue layer?
A what?
Is that the untrue layer?
True layer? No. Oh, yeah, maybe I haven't.
It's kind of, it looks like Atrus or something like that for convolutions.
Oh, that's the thing with holes.
Dilated. I think that's more for like dilated. I might be wrong, but at least that's what I saw in comparison. That's what it meant.
So, in some sense, breaking dropout or breaking backprop works because it makes it's like doesn't make your model try as hard as fitting your data. So it's similar to early stopping and similar to other ways of crippling your optimization. When you break backprop, you're not going to be as sensitive to your training data because you won't fit it as well. But the question that's not answered is why can you unfit your training data? So as you recall, you need two things. One, you need to be not very sensitive to your training data, but two, you actually have to fit the training data. And it's an open question to figure out why you can do those bad things to your optimization procedure and still be able to fit your training data. One interesting paper that came out is called Synthetic Gradients. And what they're doing is they're essentially they're taking backprop and they're saying, so when you're forward propagating, you do it as normally. When you're back propagating, for instance, to this layer, you're essentially replacing this all part of this model with a linear function, something like x. And then backprop is extremely cheap and easy, and it's called synthetic gradients from DeepMind. And it seems like a very drastic way of breaking backprop, and it seems to work. So there isn't much theory why it works. Okay, so I guess this part can go into dataset augmentation. So what you do is people discover that you can take an image and you can change it slightly, but in a very specific way, not just randomly, and then you will completely confuse the classifier. And a natural thing to do is to just generate a bunch of those images and throw them into your training set. And then your training set is better, is bigger, so it'll train better. It talks about so originally the way this was done is Christian Segeti, he actually optimized using LBFGS to optimize to find this adversarial example. So for each example, it was actually a lot of work to find this example because it used many iterations of an optimizer. A thing that became more practical later that Ian Woodfellow came up with is using this virtual adversarial examples. So the idea is you take this example and then you just compute the gradient with respect to classification, essentially trying to see, essentially you take a single step of optimization towards your adversarial example and you use that. So that's much cheaper than using just a single step of optimization. And you can look at it as essentially also breaking your optimization. Instead of taking the regular gradient descent step, you're going to take the gradient descent step for this new example. So you're not trying as hard to fit your training data. Yeah?
So he takes a photo of the panda and then the gradient with respect to the the classification activation, that would be a given, which is another category, and then backprops that back to the image and we get the image on the right.
So it takes the gradient of a panda and then it asks, how can I modify this image to make it a given? So so you get this, that gives you a gradient.
Gotcha.
And essentially, the virtual adversarial examples is that instead of using, so now, if you use the original training set, you have a panda and it's labeled panda. In the virtual adversarial example, you take a panda, you modify it to look a little bit more like gibbon, and then you use that example. So essentially, you are sort of messing with your training set and not trying as hard to fit it, but as a result, you generalize better. Okay, I think that's all the slides. Yeah, that's all the slides I have. There's the last section, 714, but I won't go into it. Yeah.
So it seems data augmentation helps a lot, at least in vision, and for neural nets. Does it help a lot for classical ML or previous approaches? Is it as important, or is it critical just for deep learning?
Well, the thing is, with vision, it's very easy to come up with data augmentation. If you have classical machine learning, you have some data set of expert features. It's not clear how to modify it. You can add noise to your input, like a Gaussian noise. But I think that may be equivalent to regularizing your parameters. So I haven't used it much for the classical machine learning. Yeah.
I remember when we read the adversarial, like you can like adversarially attack neural networks, and I remember talking with my colleagues, and we were like, would there be like a form of terrorism now where you would like run into the street and like hold some like noise, and then the car would think you're like a stop sign or something like that, and then just stop in the middle of the street?
Well, yeah, people actually found this universal adversarial images, which would confuse classifiers trained on different datasets or different subsets. Anyway, there's a lot of somehow this just blew up, this adversarial examples. So yeah, so I guess it's pretty important for security.
When you were talking before about dataset augmentation for like computer vision models, if you're trying to do something for like object recognition for like doing bounding boxes, and you like just took what was in like one object and then dropped it into like a new image, have you seen people try to do that?
Wait, take.
So like if you took a picture of like this soda can or whatever, and like in this setting, you can turn it into like 20 other images by taking the bounding box around the soda can, and then drop it into like new backgrounds. Have you seen people try to do that or no?
I guess it makes sense.
But the neural net might start learning about how you exactly drop stuff into back.
Yeah, so that's going to be my follow-up question. What people do to like learn that.
Yeah, I guess if it's like has hard edges, then it would be. You have to like drop it in a way that's natural.
Did we miss anything from the chapter? Is there something that like we didn't discuss and somebody has a question about?
So not from the chapter, but there's a popular paper at ICLR, I think this year, that said kind of understanding deep learning requires rethinking generalization. And I don't know if you have an opinion about
I haven't read it, but I remember it being very controversial.
So it seems they can learn, like they can always overfit. So basically the models seem to be over-parameterized, but they still generalize well. And then
But what do you mean by overfit? Isn't that kind of against the definition of overfit?
sorry, so they can learn the training set perfectly, where the training set is normal images and just random labels, so not real,
I see.
like nothing to do with. So there's some assumption that these neural nets are good for vision, but if you just put random labels, then it seems they can learn it. So it's not, they don't model the natural world. They can learn anything, like memorize these labels.
But how do they do on the test set?
So they have different composition of the test set. So I mean of the training set. 10% noise in the labels or 20% noise in the labels, and it still does pretty well. I mean, when it gets noisier and noisier, it does worse and worse. But it seems so it's not super regularized so that you can't get the 100% on the training.
It seems also an issue of small data sets. So if you have a real large data set, it's actually quite hard to get 100%. And also dropout makes it a lot harder to use to do it. So at Google, we typically on larger data sets we didn't use dropout because it just makes training 5 times longer.
With data set augmentations, there's some intuition around manifold learning and whether the additional examples are helping with the manifold learning.
Well, my intuition is that it's just if you augment your data set with images, if you have like this panda, and you add a bunch of images which look like panda, but the algorithm doesn't classify well, you're just making your data set bigger, and bigger data set is better. And you're making it bigger in a non-trivial way. If you just had a bunch of copies of panda, that would help, obviously. So I view it as just basically making your data set bigger and constraining your learning problem more.
If we use the mapping transforms, it's like maybe you can. There's an intuition that if you, for instance, classifying like process spaces, you know that if you like the profile peak turns in like this direction or this direction, it's not actually there's no difference. You are teaching even if you have like just for instance our profile picture in one direction profile, it's reasonable to make the mapping transform and to add it to the data set. So neural network will understand that actually there is no reason to train that other, for instance, image like other different. So if you, for instance, recognize, there is a challenge in Kaggle that was challenge to recognize from satellite images some big ones.
Farms?
Yeah, whales in the oceans. Yeah. So it's actually like the problem isn't augmenting the data set because there's some really small, and you need to find a good way to augment it in a that your data set. So you will understand that even if in a different direction it's filmed, it's still a whale. So, and in general, if you are able, so the more your, as practical my experience shows, the more the data set is augmentable, the more you can rely on deep learning. If there is something, even if, like in my company we do text mining, we have text processing, even in text that it's really hard to make this type of things. But even if there you are like able to make your data set better in terms of augmenting it, that it's a good sign that you can solve it.
Just to add on that, I come from more of like a digital signal processing background, so for anything for data set augmentation also works with like speech signals. So you can apply like varying levels of artificial reverb, varying levels of artificial distortion to speech to train like a classifier to like denoise a signal or something like that too.
Yeah.
In your own practice, what do you like to try? Like, what's your kind of order of operations that you like to try first? Do you like to try data augmentation first, then drop that, or break, or increase L2? I mean, is there like a certain kind of recipe that you like that you find useful?
I mean, dropout is pretty one of the first things people try. So let's see. So dropout. So if your data set is images, then definitely augmentation, because it's easy to. I have like this Python thing with 20 different ways to distort images. If the data set is not images, it actually can be pretty hard. So if you have text data, I'm not sure how you would augment text.
Since we are dealing with the job description, and it's like there is some invariance in job description that you can augment. So you can get, if you never write a lot of people's skills or people have records, you can make a lot of invariant people in job descriptions. But it's actually just it's not like easy to do.
Yeah, so I guess those are the two main things. And then if it doesn't work, then you can do something more fancy like this virtual adversarial examples. and then you could go to more fancy things like virtual adversarial examples. Also, I didn't talk about it, but he also talks about this virtual adversarial.
Virtual adversarial.
Yeah. Also something I think I skipped. Talks about adding noise to your weights. And also he talked about potential penalizing the gradient. So adding a gradient of your objective function as a regularizer. So there's some fancy regularizers you can use. So typically you really need to spend a lot of time on this if you have a small data set. So the smaller the data set, the more people think about regularization.
On that last notion, the gradient of your objective function as your regularizer, can you talk through that conceptually, like what that would do?
Well, no.
So like, I think that's a really important one that a lot of new research, like with the new kind of formulations of GAN, they're using, like you kind of guarantee Lipschitz continuity if you are regularizing your gradient. So like, you're changing how fast your model is updating, but I was curious if you had any intuition. Like, I think it's a really out there concept still. If you had any thoughts on
So in the book he talked about penalizing, so preferring a model which does not change a lot. So he had a penalty. Somewhere in this chapter, he talks about having a penalty which measures how fast the function is changing at a given point, and having that as a penalty. So is that similar to this GAN's?
I think so, but it's like a really bizarre thought because it's kind of recursive. Like you don't want your model to learn too fast. You want your model to be structured that it doesn't want itself to learn too fast.
Mm-hmm.
There's a drawing in the book where they said if the gradient is too high, it might jump on a cliff. So I think Ian did some practical studies on small networks, and if you do the small step, you don't jump on the cliff and then jump further out, but you kind of still go that direction towards the valley next to the cliff. So I don't know if so that's the gradient clipping one.
I think that's so gradient clipping was like, one thing where you're just not doing your full step, is then there's some other formulations where you're like actually penalizing the norm of your gradient but still doing your full step. And I think it's I don't know why it would work, but it seems to.
So the thing I was talking about, you can have a penalty which looks like this. Expected value of a gradient. So this is the term he did, and yeah. So you're penalizing by seeing how fast. So essentially, this is high when your predictions change quickly with respect to weights. So if you perturb weights a little bit, the predictions change a lot. So that's the penalty, and then it shows that you can do this explicitly, but an alternative thing is when you're minimizing, you just add noise to your weights. So you add uniform noise to all of your weights, and that will implicitly result in minimizing the subjective. Okay. Any more questions?
Good. Okay.
Okay.
I guess we can finish early. Thank you.
Good. Oh. Good, how are you? Are you still, I thought you were here are you here permanently?
But for a long time.
For a long time?
For a month.
But you left and then you came back?
Yeah,
Okay.
yeah.
Okay.
Since then, I was 6 months. I was not here.
Oh, okay, I see.
Just so
Yeah.
So basically, stress for example, 2 minutes, and this kind of thing. Then it improves stability and improves the This is what it's generating.
GANs, no, this is just adversarial training. GANs is, I guess, when you try to reconstruct. So it's applying adversarial training to reconstruction. So that was classification. What is similar to adversarial?
So basically, all this regularization is some different ways to support it, right? So add some student, but you can control it. Add some kind of science to it.
Yeah, or non-mathematical. You know, this breaking back problem. One of the words is mathematical.
If you write the formula, it's going to
variance and stuff. You might mention earlier.
Variance?
Yeah, so like variance of like your error and stability of a model. Because intuitively, I think bagging reduces variance. And I see how
you know,
it affects.
bias would be variance.
Yeah, that's the one.
So variance, so variance is a measure of how many examples. So variance, essentially, if you increase your dataset size, your error goes down. So I guess variance is how fast this goes down. So if your model has high variance, maybe like this, low variance, just variance. So this is
So, okay.
so this is
So, would you say that like stability is in case they're like gradient variance?
so stability is how sensitive it can be to data set. There's probably some connection.
So I was speaking to the person last week about, so I have a particular problem where I'm using bagging as a form of regularization. It's working great, but I haven't tried boosting yet. So what do you think about like using boosting with neural nets? Is it something that I don't know, because
I don't know, I guess depending on the problem, it has to be a pretty unusual problem because people don't use boosting.
yeah,
The question is, well, you would use when you have overfitting. So do you have overfitting?
yes. I have, so I have a very small amount of data, so I have like vast formula, some text, Oh well, yes, very small corpora of text, but they themselves, each one is very vast and you need to predict like 48 features. So it's a very like noisy problem. So I figured bagging would be a great way to like get rid of the noise and like have 50 models and have all of them average in a way. So that's what I was thinking about.
Yeah, I wish it, it's not kind of weird to use mostly with neural. I mean, I know people have done it.
Yeah.
But also if your data set is small, are neural networks really the right answer? So it's another.
The original question I was going to answer with that is embedding the like all of the data on like a different dimensional plane with the other one, like text embedding. But I don't think I have enough data to do text embedding, let alone neural nets. So I wanted to see if like.
Oh, what if you do pre-training? Is there like a similar task you can pre-train on? That's a big one. If you do like, if you have a model which, so what kind of task would it? You have to classify text? Or?
Yeah, it's inherently text classification, but the idea, it's almost a regression problem because like given some corpus of text, you want to predict whether somebody is like pro-abortion, con-abortion, gun law, gun freedom, something along those lines.
I mean, there is already sentiment analysis data sets out there. There's somebody scraped a bunch of, I think, IMDb reviews and labeled them, are they positive, negative? So for neural networks, the ideal is to just take as many related data sets as possible and just train something that works really well on that, and then take that model and just fine tune it on there. Yeah. So I've seen people do image classification with just 1,000 examples, which work pretty well by taking the image and classifier and fine tuning.
Just freezing, depending on how many like examples you have, like freeze some early parts of the network and then only train the last like two layers.
Because at least with
You like a transfer.
Yeah, that's what I was thinking about. Also, quick question. So I'm just starting out in this space. So would you suggest? So I was at Regularization last weekend, like Android small things, like implement as many papers as you can. Would you suggest going down that route or like starting from the basics, so like elements of statistical learning, the deep learning work, so on?
Yeah, I mean, there's so many basics. You can just spend 8 years just doing basics. I think the best is to just do it, and then when you have something basic, just fill in the gaps, and then eventually you'll fill in the relevant gaps. Yeah, a lot of the things like elements of statistical learning, a lot of the theories they talk about here is not really relevant. For instance, the L1 panels, people studied, one thing I remember, people get really excited about the regularization task. So what happens if you change you have the L1 panels, and then you have lambda, depending on the value of lambda, you have a different number of parameters that are active. And people get the whole thing, so you do them, and some parameters are going up, and then another one going up. And people spend a lot of work figuring out how to compute this efficiently, but it's not really relevant. But this is elements of statistical learning.
Yeah, that's the first 150 pages. Any papers you would suggest starting on that are particularly interesting?
I guess it depends on your application. If you're doing text, I haven't done much more vision.
So like I found the interesting one I found in vision was the style transfer one, but I wrote my implementation on that one, but like that's pretty much like where it's stopped. So where would you suggest going?
Well, what's the goal?
Just learning as much as I can. Like I don't have a particular mind.
I mean, Reddit machine learning seems to be pretty good for like the tech papers which are popular. There's some discussion there.
Oh, just Reddit's machine.
R machine learning. Yeah, I guess you want to implement papers which are popular because then
Just get it checked.
well, then it would be like something that people care about.
Okay.
Yeah.
Thank you.
Yeah.
Were you using like a open source thing for doing like the like data augmentation for images, or you wrote
For the text, I was using Yaroslav as this paper with this experiments.
Yeah.
And I took that's the first code.
I can walk out.
And then I had a router that came in using Python.
Yeah.
You just come in and write.
Yeah. So there's like a repo I just found today was have like kind of like the same thing, just a small bits, and figure out how to make the most of it. We're like just detecting like objects for doing one of the biggest things that I was thinking was I don't want to take a trip into your time.
Yeah, maybe I don't know.
Oh, wait.
Yeah, I'm actually waiting for the question.
Okay, cool. Yeah. So yeah, one of the problems I was having is like I just randomly sampled like images to use and just look at them for like training, validation, and testing. And some of them were so similar they gave me like a false sense of like doing well, you know what I mean? So yeah, now it's kind of one of the other questions.
So at least the last 100 last 10,000 examples were actually really fast. So it's not So ahead of the show, I was trying to create classified images on the table. So we scraped it with downloaded all the fonts on the internet. And then we're getting suspiciously good results. It turns out it's actually a hard problem. How do you make sure you don't have the same example?
Yes. So what would you do to like to compare them? Right now I'm trying to compare like RGB Instagrams and saying like correlations. And so it's a bot to make sure that like consistent images is always in stable.
Well, I guess instead of like an application, what you care about is how well it will work in a application. And if there isn't an application, then you care about putting enough effort so that people don't, when you write a paper, people don't say it's wrong. So what is it happening?
Yeah, it was just like images that could be like 10 pictures of like it's just like just random. It's the same set of elements. So it's just like
This data set so maybe better split.
yeah, so it was just like it didn't come split. It just came with like the images and then like the annotations. But if you just randomly split them, then it wouldn't give you the false.
Ideally you would use some kind of thing like I guess I am for someone else. So I don't know. Similar data set specific.
But do you have anything you would say to compare like they didn't have timestamp, it was just like two images, how would you decide if those are two similar images as separate like data sets?
You could like draw the big guns and with that model use fast analytics, which are video k-means, and then you use different buses.
That's clever, yeah. Yeah, I guess I pull out the big ones again. That actually that wouldn't be like that much work on my end, because I can just take that. Do you have any like intuition in this time when you guys huge list. But it's like an intuitive understanding of why the rest of that's actually just like papers doing that with like symmetry or something like that. Made it you could do well, but I didn't do that.
Identity matters.
Yeah, that's the one. Yeah.
So actually that makes sense. So basically, what they do is when the weights are zero,
Yeah, it's an identity.
So,
an explanation. It's very tough.
and then you penalize by the square order or W. Essentially, everything again here. Actually, the theory shows that you can gradient descent actually define the global in a given resonance.
Really?
Yeah.
I think that this one, the paper I'm talking about might have run it live. This one came out like in April. Yeah, no worries.
I'll have to slow one.
We're embedding, like embedding.